sense of previous talks, I have no need to say some introductory words about the various materials, but I would like to talk about some dirty things that can be done with them. Let's go back around 10 years when graphene just appeared on the scene, and at that time there was fabricated a device like a common field transistor, and in experiments it was found that the conductivity doesn't drop below some certain minimum. Because of that, there are speculations that we have massless charge carriers in graphene, and therefore they cannot be localized by any imperfections, any impurities that are contained in this system. Even more, it was claimed that the physics of semiconductors should be rewritten from the scratch for such materials because they have a unique behavior due to the linear dispersions of electrons. And indeed, it was an interesting point why we have such minimums that don't go up to zero. Just several years later, it was found that probably the behavior is not such universal as it was thought. So the resistivity was found to be strongly dependent on the sample, on the kind of preparation, and even more, the minimum of conductivity was located at a different gate voltage of the field transistor. Is it possible to apply usual ansatz that goes to the semiconductors to such a system? And I will try to do this. So let's consider the simplest problem, which tackles the impurities. This is the tie-binding model of the system, which works well for graphene, but we also will add some impurities in the so-called sometimes Lynch's model, or sometimes it is called diagonal disorder and binary alloy with diagonal disorder, when we just assume that impurities are located absolutely in random on the lattice, and what they do, they are just changing the potential at the site where they are located. Probably nothing more simple can be devised. So here we have Hamiltonian that is divided into two parts. So H0 is the host Hamiltonian of a clean system, and we have some impurity perturbation, and here is the change of the potential at the impurity site, and summation is carried over those sites that are occupied by impurities. As for H0, we can adopt the usual nearest neighbor or something, and of course there is a transfer integral, and we can linearize spectrum nearby direct points. But this is just the problem that we should solve. And now some historical parts about how such problems were solved before. One of the usual approaches is to find the average Green's function for the impure system. In the system with disorder, we just average over all possible distributions of impurities and then calculate the Green function, which is actually a self-averaging magnitude. To do this properly, it is probably easiest to introduce the self-energy, and a long time ago, Langer devised a so-called modified propagator method, where the possible simplest single-side diagrams were summed up. So the diagrams which appear up to the first power of the concentration of impurities level C here. Later on, we had a well-known and widely used coherent potential approximation, where all the single-side diagrams were summed up, but we will not need these actually, because the difference, as you see, is only with the self-energy that enters nearby the perturbation, and when concentration of impurities is rather small, and we will consider only this case, in fact there is no difference between two approaches. But the question is, how appropriate is the modified propagator method or the coherent potential approximation in a disordered system? And we cannot say that it works well at all energies, in all portions of the spectrum, and it was known from the beginning. But how to know where we can use it, where it is adoptable, or where it is not? Actually, we should look at the series for the self-energy, where we expand it in all possible impurity clusters. So we have the first one, contribution, which is linear in impurity concentration, and this will give the modified propagator method. Then, second contribution, this is actually the beginning of those diagrams that goes then for coherent potential approximation, and they can be omitted because of the low concentration of impurities. But the most valuable is the pair term and higher order term of clusters containing 3, 4 or more impurities. These pair or larger cluster scatterings can become prominent and actually dominate. So every time we should check if we can restrict ourselves just to a single side theory or not. And this is only the question of the CPA or modified propagator validity at this point. But there is a second step, and initially it was seen that nearby the band edges or nearby any one-hole singularity, the CPA doesn't work well. And it was known that indeed this is because the cluster imputer scattering that becomes important. At that time, Jukasted devised the criterion that this quantity, which becomes exactly 1 at the CPA band edge, should be treated like some kind of criterion of the CPA validity, and if we approach with this criterion to unity, then something will happen, so the CPA is not valid. At that point, it was not so much clear where from comes this magnitude. But if you look at the series for the self-energy, we can see that there is a small parameter in it, and this parameter is just the loop interaction. And in fact, this loop interaction, the propagator moving to the next impurity and back, multiplied by the concentration of impurities, absolutely coincide with the magnitude proposed by Jukasted. The second question is how close we can come to the unity to still use the CPA, and does it have any meaning at all? Except that we use CPA as an approximation to calculate density of stasis. It can be shown that, for example, in 3D system with a conventional parabolic dispersion, this parameter, this small parameter of this criterion is strongly correlated with the well-known Yuriy Skrypnyk criterion. they can be expressed one through other just by a simple substitution when we take renormalized energy and separate the phase and modulus. So then this criterion depends only on the phase of the renormalized energy as the Yuriy mode criterion. That means that the CPA or the modified propagator method are working well for delocalized states. And thus, we can use this criterion when it approaches some magnitude of 1/2 to separate localized and delocalized states. So in other words, with these ansatz, we can predict the mobility edges in the system, how they appear, how they move, how they evolve, just from the single particle Green's function. So for that, it is easy to see that what we need is just the diagonal element of the Green's function, and the systems that have similar behavior in Green function will behave similarly. Is graphene somewhat different from conventional systems? Well, it is. We can consider a kind of effective dimensionality which depends on the dimensionality divided by the power in the dispersion law, power of the wavelength. For low-dimensional systems, we have this parameter that is smaller than unity. And then we have a transition to a 3D where it is larger, and in this case, for the parabolic dispersion, the 2D system is a marginal one. And for graphene, we have, because of the linear dispersion, this parameter equal to 2. So this means, in some sense, graphene will behave like a 4-dimensional system, so probably it will be harder to localize charge characters in it. But in the title was something about the band structure transformation. What is that? And I would like to say that this is a common phenomenon common to all disordered systems. In the case we have impurities, they form impurity states. And these impurity states, of course, have the effective radii. So, at some concentration of impurities, these impurity states should overlap one with other. And after that, we expect some crucial changes in the structure of the spectrum of the system. That means that we will have a Riemann gap in the spectrum that opens up, or we will have a transport gap that is filled with some states, or in reverse, there will be a band, new one, appearing with delocalized states. But for all that, we will have some critical concentration at which this happens, and this will be the critical concentration of band structure transformation. The question is, can we apply this ideology that works well for ordinary semiconductors to graphene? Let's take a look. So if we will have just one impurity, isolated, we can easily calculate the local density of states at the impurity site, and we see that when the potential of the impurity is rather high, then the shape of this curve is just a Lorentzian, and we can talk about the well-defined resonance state. What does this mean? This means that the energy of the resonance is located somewhere close to the one-hole singularity, in this case direct point. But the damping is smaller than this distance. So the definition of the resonance is well done in this case. In a turn, this means that if we will have the energy of impurity resonance, then we will have a characteristic energy of the impurity state and can devise from the behavior of the Green's function of the host system the effective radius. And this is, of course, 1 over the energy of the impurity resonance. Then, very easy. We just calculate the average distance between impurities and compare to magnitudes and have some critical concentration, that is the square of the resonance energy. Of course, it is dimensionless in this case. Well, this is very crude estimation. But if we go into more detail, then we'll have nothing much different from that. In fact, yes, we can obtain the small parameter of the series, or our testing magnitude, which shows us where the mobility edges are located in our system, and then try to find them. And then we find that there are two regimes. One regime is when the concentration of impurity is smaller than the critical one. And in this case, graphene with impurities behaves like a very robust system for the impurity perturbation. The result is actually unique for the disordered systems. We have that the width of the transport gap that follows from this criteria is exponentially small, so probably non-existent in some sense. If you compare that to conventional low-dimensional systems, we have some power of the impurity concentration for the width of this transport gap that usually appear at some one-hole singularity. And same goes for 3D system when it is the square of impurity concentration. Sometimes this width is called the concentration smearing of the bandage. And in our case, the Dirac point plays the role of such one-hole singularity, the role of the bandage. Why we are talking about this critical concentration? Because if we will turn back, then we will see that the impurity resonance energy can be quite small, and because it is located very closely to the Dirac point. And then our critical concentration will also become small, and we can expect that with increasing the concentration of impurities, but still having the concentration of impurities quite small compared to unity, we can expect a kind of band structure transformation, and after it we'll have absolutely different behavior. The transport gap will be more wide and will be widening with high speed with increasing the impurity concentration, because it is proportional to square root of impurity concentration. It will cover initially the energy of impurity resonance and spread, covering large space. Actually, it can easily cover all the interesting space for Fermi levels in graphene. If you will calculate very simply using this modified propagated method and Kubier formula the conductivity of the system, then we will have interesting result. We have the minimum of the impurity conductivity not at the Dirac point, but at the energy of impurity resonance. Of course, this can be done only close to the energy. This can be done only when concentration of impurities is below the critical one. And when we are approaching it, we see this flattening of the curve, which means that something wrong is going with the system. Actually, what is wrong? We performed numerical calculation, and you see here this line represents this small parameter which shouldn't be larger than 1/2, unless we predict that states are localized. So, of course, we have calculated density of states by the Dean method for large system, and we see that in the predicted interval, it deviates quite strongly from the CPA result. And if you look closely at the states, we will see by using the West participation ratio that for high concentration of impurities, we have strongly localized states, which contrast to the low concentration of impurities compared to the critical one. And these localized states, of course, can be identified, and they are localized, for example, nearby the pairs of impurities, and the radius of localization is just several lattice constants, or more widely spaced. These states correspond to this one and this one peaks. There was an experiment where hydrogen was deposited on the graphene, and its concentration was steadily increased. What was seen at the RPS experiment, that nearby the Fermi level is increasing the concentration of hydrogen. There is a gradual smearing and loss of the Fermi liquid picture totally. So indeed, in this experiment, we see that there is an evidence for the localization. And same follows from the calculated mean-free path from RPEX and the gradually reducing wave vector because hydrogen acts as acceptor in this case. And also, they saw in the experiment some strange upturn of the dispersion of electrons, which they mentioned earlier, of course, the Brody. So can we use our simple picture to explain this? Yes, of course. So if we just use the simplest Lifshitz model, then we obtain absolutely similar evolution of the EDC curves. And even more. This is the concentration of, this is the spectral function, the density plot. And this is the concentration of impurities that are just below the observed metal insulator transition. And here is just above. You see that the Fermi level, which is at the top, appears in the region of the localized states. So how in this case the metal insulator transition is explained? As the concentration of hydrogen increases, then we have opening of the transport gap nearby the resonance energy. And after that, this transport gap widens and Fermi level is lowering gradually, and so the mobility agent Fermi level intersect. And even this simplest model can explain this experiment actually semi-qualitatively. The second experiment, which is interesting in this case, was the experiment done by Ponomarenko, and this is about the metal insulator transition in the sandwich with boron nitride. In this case, they placed the additional graphene layer just to eliminate any possible puddles due to the charge inhomogeneities in the substrate. In the testing layer of graphene, what they found that if the temperature is quite high, we don't see any features, but if the temperature is low enough, we can see that the resistivity of the test layer increases rapidly when we inject some charge characters in the top layer. So when our puddles are eliminated, we can see the metal insulator transition in this system. And this is the comparison of two behaviors just in one picture. So in this case, with lowering the temperature, the resistivity can go up to huge numbers compared to the, well, several kiloohms to megaohm. And this can be again tried to be explained from the above presented picture of simple Lipschitz model. Let's imagine that we have some strong scatterers, for example vacancies or something like that, probably hydrogen, and then we can estimate the amount of impurities that is present in the system. So then we have that crudely the threshold magnitude for the charge carrier concentration should be around the concentration of impurities in our system. We can perform a little bit more rigorous estimation. So we have in the result that the concentration of remaining impurities is quite small, and this is a remarkable experiment because of that. But probably we don't go far enough to the stage when we can see the exponentially small transport gap, because still graphene attracts a lot of impurities and cannot be made perfectly clean. There were numerous experiments on graphene with embedded defects. One of them is when these defects were done by ion bombardment, producing vacancies, and there also the metal insulator transition were found even at room temperature when the concentration of vacancies was around 0.5%. So finally, afterwards, that massless charge carriers cannot be localized by any means, by any impurities. And this year, there was a publication with the title, meaning the functionalized graphene is a model system to study the metal insulator transition. So let me conclude that if we will consider the impurity effects in graphene, so then we can say that novel picture of semiconductor physics stating that there should be band structure transformation works well, and we can specify a critical concentration of impurity at which it takes place. And then this critical concentration of impurities indeed follows from the special overlap of the impurity states. And of course in graphene, this band structure transformation results in the opening of the quite wide transport gap in the system. Thank you for your attention.